Hello friends, welcome back to this session on bi-connected components in graph theory. Okay, reading out the definition, a bi-connected component, also called as a bi-connected component or two connected component, is a maximal subset of a graph such that the subgraph is connected and removing any single vertex or its edges does not disconnect the subgraph. Point to be noted. In other words, a bi-connected component is a part of the graph where no single node acts as a critical or bottleneck for communication. So, understanding the definition, a bi-connected component is a part of an undirected graph. So, this bi-connected component is a part of undirected graph. Point to be noted. The part stays connected even if we remove any vertex. Removal of any vertex does not affect the graph. Okay, it does not have any weak points. Also called as cut vertices or articulation points. So a bi-connected component does not have any weak points like cut vertices or articulation points that would break the graph into pieces if removed. Okay, this is the concept of bi-connected components. So running through key concepts once again. A graph is bi-connected if it has no articulation points or weak points, as already discussed. An articulation point or cut vertices is a vertex that, if removed, increases the number of connected components. We'll look into the example now in the graph. So articulation point or cut vertex is a vertex that, if removed, it increases number of connected components. A bi-connected component includes vertices and edges such that all paths are robust or fully connected. The structure can withstand the failure of any one node. So, bi-connected component can withstand the failure of any one node. It will not affect the connectivity. Example. Here, in this example, this is not bi-connected component. This is not a bi-connected component. First, we'll look into the example. Considering a graph A, B, C, and D, in this structure, in this case, vertex B is an articulation point or cut vertex. Okay, because if B is removed, then two connected components are formed. Okay. If B is removed, A is component 1, C to D is component 2. So B is an articulation point or cut vertex. Removing B, it disconnects the graph into two parts. The bi-connected components are now A and CD. Okay, component 1 and CD. Each component forms a subgraph. This is one subgraph and this is another subgraph 2. So now considering another network, that is A to B to C and again to E. In this case, there are multiple paths between nodes. Multiple paths between nodes. Okay. If we remove any one node, if we remove any one of the node from A, B, C, E, the rest of the graph still stays connected. Removal of one node still stays connected. It is not differentiated or forming subgraphs like this in this scenario, case 1. It is not forming subgraphs as in scenario 1, case 1. So this is a biconnected component. This is a biconnected component. Okay. What is the real life analogy of biconnected component? Real life analogy of biconnected component. Think of a building with multiple exits. Building with multiple exits. Okay. Even if one door gets blocked or closed, one door closed, we can still leave the building using other doors or paths. Other doors or paths. Okay. This is an example of biconnected component. It is safe and robust. Okay. So, why are biconnected components so important? To help identify critical points in the network, whether there is any dependency or not, when failure would split the system, where if the failure of one node will split the system or not, to identify critical points, and if the failure of single node will split the system or not. Okay. So, applications or use cases. In communication networks, they help us find areas that are not vulnerable to single point of failure. Okay. In computer networks, areas that are not vulnerable to single point of failure. Okay. To identify areas that are not vulnerable to single point of failure. Okay. Even there is a single point of failure, the connection should work. Okay. The connection or communication path should go on. In circuit design also same, ensuring redundancy, there should not be any failure. In software systems, they help locate fragile components. In software architecture, it locates location of fragile components that can disrupt connectivity. That disrupts connectivity. Okay. Next, in biological networks, they can highlight resilient subsystems. So, studying robo systems and biological systems and highlighting resilient subsystems. Okay. So, how to find biconnected components? So, we are going to see few concepts here. How to find biconnected component? If it has articulation point or cut vertices where there is a dependency, we need to find whether they have any articulation points or cut vertices for the biconnected component or not. We use modified depth first search. So as we have already discussed, depth first search algorithm go to the child networks rather than the neighboring networks. Okay. So keep track of discovery time and load time for each vertex. Now we have the concept of discovery time. So what is discovery time? When you visit a node using depth first search, when you found it, this is discovery time. For example, you are searching for a node D. When you visit a node using depth first search, when you found it, this is the discovery time. So finding D is the discovery time. If you reach node A at time 1, discovery time is 1. If you reach, for example, if you reach a node A at a time is equal to 1 second, then the discovery time is 1 second. If you can go back to node 1 from child, load time is equal to 1. Load time is nothing but, for example, if I am traveling from A to child node D, and again I am going back to node 1 from the child, node 1 from node A from the child, then the load time is equal to 1 second. Okay. So what is the concept of another thing, that is back edge? Use a DFS tree, depth first search tree, to detect back edge and articulation points. So as you go and move from one node to another in DFS, you are creating a tree. Here we are creating a tree. Sometimes you can find edges that goes back to an earlier node. In this scenario, we are going back to an earlier node. That is called back edge. You can find edges that can go back to an earlier node. For example, if I am traversing from C to F and again going back to an earlier node C, this is called back edge, and the time is known as load time. These help check if nodes are connected in other ways besides direct child. Okay, this also helps check if nodes are connected or not. So a node is an articulation point. So what is our main agenda? To find out articulation point, because if there is an articulation point, it divides into subgraphs or subconnections or subcomponents. That should not be done. So to find out biconnected graphs, there should not be any articulation point, no articulation point. As we have discussed here, a graph is said to be biconnected if it has no articulation point. So if we found any articulation points, that is not a biconnected graph. So how to find a node is an articulation point? Rule 1, here we have two rules. Rule 1, excuse me. Rule 1, if a node is the starting point or root of the DF, if a node is the starting point, we'll take another example. A, B, C, D. So if a node is the starting point, root of the DFS, called root of DFS, and has two or more branches, then it is an articulation point. Because removal of A removal of A breaks the graph into two subgraphs. If there is a removal of A, what happens? It is divided into B and C to D subgraphs. So then A becomes the articulation point. Root of DFS is an articulation point. Thumb rule 1. Okay. Rule 2. What is rule 2? For any other node other than root, if any one of its children cannot go back to an ancestor, then the node is an articulation point. Okay. If any one of child can't go back to an ancestor, then that node is articulation. Okay. Now check C in this scenario. In this scenario, if we remove C, case 2 or rule 2, if we remove C, D cannot reach A or B. Then C is an articulation point. Okay. What does rule 2 say? C is not a root of DFS. If any one of the child, if we remove C, the child cannot go back to the ancestor. That node is called articulation point. Okay, this is rule 2. Hope you got it. So, how is this biconnected component detected using algorithms? The two major algorithms include Tarjan's algorithm, linear time, and Hopcroft and Tarjan algorithm. Both these algorithms are used to find important structures in the graph, like both these two help to find important structures in a graph. Identifies important structures in graph, like articulation points, which is very important in biconnected components. First thing, and second thing, bridges, edges that removed disconnect the graph. Bridges are edges that removed disconnect the graph. Divide the graph into subgraphs. And finally, biconnected components. All these can be identified using these two popular algorithms, 1 and 2. Okay. So finally, again going through the video, a biconnected component is a graph. Is a group in a graph where no single node removal can break the connectivity. Point to be noted: no single node removal can break the connectivity. It represents fault-tolerant parts of the graph. These components help in analyzing robustness, resilience, and vulnerability networks. DFS-based algorithms like Tarjan's algorithm are used to detect them efficiently. Okay, we have covered all the points. Thank you.